Hello, welcome back to the course on application of spectroscopic methods in molecular structure determination. We are in module 18 now. In this module, we will consider certain fragmentation patterns of organic molecules under electron impact ionization mass spectrometry. Electron impact ionization mass spectrometry, the molecular ion typically undergoes fragmentation pattern, which is a very valuable thing in the structural elucidation problems. Now, in the electron impact ionization, molecule is actually bombarded with high energy electron. This collision not only ionizes the molecule, but it results in the absorption of considerable amount of extra energy by the molecule. This extra energy can place this molecule in higher vibrational state. Once molecules are in the higher vibrational state, they can undergo bond breaking from the vibrationally excited state, resulting in extensive fragmentation. In fact, the fragmentation pattern is a fingerprint kind of a signature of an individual molecule, and it is reproducible, and hence it is extremely valuable in structural elucidation problem. Typically, if a molecular ion has a lifetime more than 10 to the power minus 5 seconds, the corresponding peak will be registered in the mass spectrum. However, molecular ions which less than 10 to the power minus 5 seconds of lifetime break apart into fragments in the ionization chamber itself before they are accelerated. But then not all molecular ions formed during ionization have the same lifetime. Hence, some of them will be fragmented and some of the molecular ions will still get registered as molecular ion in the mass spectrum. Fragmentation process is always a unimolecular process because the concentration of the gas phase ions are so low that intermolecular collision is very unlikely. That is the reason one says the fragmentation process is always a unimolecular process under mass spectrometry conditions. The molecular ion is actually obtained by knocking off an electron from the organic molecule. Organic molecules typically have even number of electrons. Therefore, when it is ionized to a cation radical or an anion radical, they become odd electron species. That is why they are called the radical cations or the radical anions. Odd electron ions have even mass if there is no nitrogen present. If they have a nitrogen present, one nitrogen or odd number of nitrogen present, then it will have odd mass. And the fragmented even electron ions will have odd mass. This is something we can see in practical terms when we consider the fragmentation pattern of various molecules. The most probable fragmentation is the one that leaves the positive charge on a fragment with the lowest ionization potential. This is understandable because the ion will be stable ion. It is the most stable ion that is going to be resulting in the fragmentation pattern. So one can even predict the fragmentation pattern based on the stability of ions, based on the electronegativity, polarizability, resonance stabilization, octet rule. All this can be applied towards the stabilization of a particular ion. So it is possible to predict the fragmentation of certain class of compounds, organic compounds. There are two ways a molecular ion can fragment. The first mode is essentially cleavage of a single bond to produce even electron odd mass fragment and a radical. This is illustrated in this example. If we take the benzyl bromide as an example, the radical cation of benzyl bromide will have two molecular ions because of the bromine, 170 and 172. This is an odd electron species because it is a cation radical, but the masses are even, you can see here. When it undergoes the fragmentation to get rid of the bromine radical is produced. The resulting ion is actually an M by Z value 91, which is an odd mass, and it is an even electron species because one of the electron has gone with the bromine. So the cation radical, when it undergoes a fragmentation process in this particular manner, it produces an odd mass and an even electron species. This is what is meant by the statement, cleavage of one prod produces an even electron odd mass fragment and a radical. Let us consider the case of tertiary butyl benzene. Tertiary butyl benzene, one of the carbon-methyl bond can be broken, resulting in the formation of a tertiary cation, which is a stable cation. Similarly, here also the benzyl cation is a stable cation. That is one of the reasons why the carbon-bromine bond is weakened during the fragmentation process that takes place selectively to get rid of the bromine to get the benzyl cation, which is a stable cation. This is a dimethyl substituted benzyl cation. It should be even more stable because it is a tertiary cation compared to this one. Once again, if you see, you start with the even molecular weight After the fragmentation, to get rid of this methyl radical, you get an odd mass which is 119. This is an odd electron species with an even mass, and the fragmented molecule is an odd electron species with an even mass. This is what is meant by this statement that cleavage can produce an even electron and an odd mass fragment. Suppose in case of nitrogenous compound where there is an odd number of nitrogen, take the example of ethylamine cation radical. Because of the presence of nitrogen, the mass is odd, but the molecular ion is also a odd electron molecular ion. So both the mass as well as the electron count are odd in this particular case. When a fragmentation takes place, in this particular case there are two types of fragmentation that can take place. In the first fragmentation, a methyl can be lost, resulting in the formation of an iminium ion which has an even number of mass and even electron count also. On the other hand, the alpha hydrogen can be removed as a H dot, resulting in the formation of a methyl substituted iminium ion. The difference between this and this is that this is a methyl substituted iminium ion, this is a simple iminium ion. This is a even electron and a even mass species because there is a nitrogen present in this particular case. The second mode of fragmentation of a molecular ion is to cleave two bonds. This typically happens when you have something like a retro-Diels-Alder reaction taking place or a McLafferty rearrangement kind of a rearrangement that is taking place. In all of this process, a closed shell molecule such as water, carbon monoxide, carbon dioxide or nitrogen, ethylene, acetylene, these are simple molecules which are released during the course of the fragmentation. Let us take the example of cyclohexene cation radical. Cyclohexene cation radical, one of the fragmentation processes is to lose ethylene to give butadienyl cation radical. Now you start with an odd electron species and you end up with an odd electron species with the removal of a neutral small molecule like ethylene in this particular case. The mass is even to start with and you end up with the even mass also. So an odd electron even mass species upon a fragmentation to release a neutral molecule like ethylene essentially ends up with an odd electron even mass kind of a species. This is true in this case. The hydrogen is migrating to the oxygen, resulting in the formation of the enol, which is registered as the radical cation, and a neutral molecule of ethylene corresponding to this particular fragment is released. We will see the mechanism of the retro-Diels-Alder reaction and the McLafferty rearrangement in a while. As I mentioned earlier, the electron impact ionization mass spectrometry fragmentation pattern is a reproducible one if it is carried out under controlled condition, typically at 70 electron volts of energy of the electron beam, which is the excitation beam. Now, if the molecular fragmentation pattern is reproducible, then one can actually create a library of fragmentation pattern of various types of molecule, and this fragmentation pattern being a fingerprint kind of a system, it is easy to identify molecules, unknown molecules, and correlate it with the known fragmentation pattern. Fragmentation process is often predictable for a given class of molecule. This is what is meant by the fact that the fragmentation takes place to produce the most stable cation and so on. Based on this predictability is what is essential for the identification of the organic molecule based on the pattern recognition. Therefore, this is useful in the structure elucidation problem. That is, the fragmentation pattern is useful in the structure elucidation problem. Now, the commonly observed fragments which are lost during their fragmentation process and their masses are given here. Normally, when there is one mass unit different from the molecular ion, this is typically of hydrogen atom loss. If there is a 15 unit of loss, then it corresponds to methyl CH3. If it is a 26 loss, then it is an acetylene molecule, a neutral molecule is lost. In these two cases, these are radicals which are lost, hydrogen radical, hydrogen atom, and methyl radical, whereas in this case a neutral molecule is lost in the form of acetylene. Similarly, for the loss of 28, which is a even mass, for example, it will be a loss of ethylene or a carbon monoxide molecule. If it is 29, it will be a ethyl group loss, C2H5 corresponds to 29. If it is a 31 loss, then it will be methoxy. 43 loss can be either a propyl group or an isopropyl group or a COCH3 group, acetyl group loss can also be 43. 44 is typically carbon dioxide. This is a very characteristic feature of decarboxylation reaction where molecule loses a molecule of carbon dioxide with a mass loss of 44. Ethoxy corresponds to 45 mass unit loss and nitro group corresponds to 46. If the halogens are present, then you will see loss corresponding to 35 and 37 corresponds to the chlorine, 79 and 81 corresponds to bromine, and if there is an iodine which is lost from the molecule, then a big chunk of the mass is gone. 127 mass loss corresponds to iodine mass loss. Now typically in the linear alkane, they produce fragments which differ by 14 mass units, because let us consider this linear alkane. If you fragment it here, methyl is lost. Subsequent fragmentations correspond to loss of CH2 groups which are 14 mass unit difference. So the lower molecular fragments are more abundant normally compared to high molecular weight fragments. Whereas in the case of the branched alkane, fragmentation takes place more readily, because fragmentation of, let us say for example, this more branched alkane essentially results in the formation of tertiary cation. So the fragmentation process is much more facile in a branched system, and hence the molecular ion is highly short-lived. In fact, if you look at the molecular ion peak of the branched system, they would be negligible compared to the fragmentation molecular ion of the linear alkanes. Typically linear alkanes show a fragmentation pattern like this. This is a Gaussian type of a thing. The most probable ions are the low molecular weight ions. If you see, each one of them will differ by 14 mass unit corresponding to the CH2 unit. This is the oil that is used as a dispersion oil for storing sodium hydride. Sodium hydride is typically kept under paraffinic oil, and this corresponds to the mass spectrum of such an oil being investigated, and it gives a peak corresponding to 14 mass unit difference all along, up to the point of reaching the lowest molecular weight of 43 or 28 or so. This is the kerosene sample from lithium aluminum hydride. Lithium aluminum hydride is also stored under kerosene because it is air sensitive, moisture sensitive. So this is again a typical fragmentation pattern of a linear hydrocarbon molecule kind of a thing. N-octane, for example, shows the molecular ion at 114, which is a small one. The most prominent peak is the propyl cation, which is 43. So fragmentation must be happening somewhere around here or somewhere around here, resulting in the formation of the propyl cation as the most abundant cation. On the other hand, if you look at isooctane, which is a highly branched hydrocarbon, the molecular ion which is at 114 is a negligible amount of molecular ion is there in comparison to the N-octane. It is even smaller than N-octane. For example, here the relative abundance is 10%, whereas the relative abundance here is only 2%. And the fragmentation results in the tertiary butyl cation, which corresponds to 57, which is the most abundant or the base peak of the mass spectrum. Cycloalkanes generally form strong molecular ion. Fragmentation requires bond cleavage at two different positions. In other words, the retro-Diels-Alder kind of a fragmentation will result in the cleavage of two bonds. Therefore, the loss of ethylene is generally very common in the case of cycloalkane. Let us take the example of norbornane. Norbornane molecular ion peak is around 96.2, and if it loses an ethylene molecule, 28 mass unit will be lost. That would correspond to 67. After that, you get the loss of ethylene molecule. Probably it will produce a cation radical of cyclopentane, for example, or cyclopentene cation radical is what will be produced. And such a molecular ion loses a cation radical, loses a hydrogen atom to give 67, which is the base peak. So loss of an ethylene unit followed by loss of a hydrogen atom resulting in the formation of a cyclopentenyl cation is corresponding to the 67 mass unit. The subsequent fragmentation produces the smaller peaks that you see here. In fact, in a mass spectrum, you don't tend to interpret every one of the tiny little peaks that are seen here. The most prominent peaks are generally interpreted with some fragmentation kind of a pattern. The rest of the peaks are generally not very valuable in the structural elucidation problem, and one does not pay attention to anything less than 20% of relative abundance unless it is a molecular ion peak. Now here the comparison of Z2-pentene and E2-pentene are given here, and this essentially corresponds to more or less an identical spectrum. You have the molecular ion peak at 70, a fragment peak which is due to the loss of a methyl group, for example, comes at 55, and there is a peak at 42, which probably comes from loss of ethylene kind of a group, because this is 28 mass unit different from the 70, and then loss of a hydrogen from this fragment will essentially give 41. A similar identical pattern of fragmentation is what is seen. In other words, based on mass spectrometry, one cannot distinguish between Z-pentene, cis-pentene from trans-pentene, which is the E-pentene, for example. So stereoisomers of this nature cannot be distinguished by mass spectrometry if they have identical fragmentation pattern. In the case of acetylene, if it is a terminal acetylene like in the case of 1-pentyne, there are two possible ways a hydrogen can be lost. The hydrogen can be lost from the terminal alkyne hydrogen can be lost, which is 1 mass unit less, or the propargylic position hydrogen can be lost, because that will generate a stable propargyl cation, and this is what is registered at 67, 1 mass unit less than the molecular ion, which is 68. So the base peak is essentially 100% abundant peak is lost due to the hydrogen atom either from this position or from this position. Then comes the loss due to the methyl group, which is corresponding to 15, loss corresponding to 29. For example, if you subtract 29 from this one, essentially you will get the fragmented ion somewhere in this particular region, for example. And the further fragmentation is the McLafferty rearrangement. In other words, here, because of the C triple bond C, it is capable of undergoing a gamma hydrogen abstraction to this position, resulting in the formation of an allene. The mechanism is as shown by the fish hook arrows. Because we are talking about an odd electron species, we always use fish hook arrows to show the mechanism rather than a regular arrow to show the mechanism. So the allene is registered as the ion corresponding to, let us say, 40. I think it is 36 plus 4, 40 is the molecular weight of this particular ion, and that is registered. And the allene loses one hydrogen to give the allenyl cation that corresponds to 39 in this case. The ethyl loss can be seen as a 29 fragment here in this particular case as one of the ions that is produced in this case. When the alkyne is an internal alkyne, there is no loss. Here, for example, loss of hydrogen is the base peak. 68 minus 167 corresponds to the loss of hydrogen. But you see here the base peak itself is the molecular ion peak, because loss of hydrogen from the propargylic position is not so much so compared to the terminal acetylene hydrogen. Since the terminal acetylene hydrogen is missing in an internal alkyne, as in the case of the 2-pentyne, for example, the molecular ion peak itself is registered as a base peak in this particular case. Subsequently, loss of 29 and 15 essentially gives you the fragmented ions which are seen in the mass spectrum. Now let us have a look at the McLafferty rearrangement. Abstraction of a gamma hydrogen by a C double bond X or a C triple bond X. In other words, a cyano group or a carbonyl group will be representation of the C double bond X and C double bond triple bond X, for example, where X can be a carbon or a heteroatom. It could be a C double bond C or C triple bond C also is capable of undergoing the McLafferty rearrangement. It is not a concerted reaction, although the mechanism normally we depict in the mass spectrometry mechanism is a concerted mechanism. It has been shown to go via stepwise mechanism. An alkene is generally lost. The fragment observed is an odd electron, even mass unit, if no nitrogen is present. This is something we have already discussed. So this is a McLafferty rearrangement. This is alpha, beta, gamma hydrogen. This is a gamma position hydrogen which is subtracted by the X, resulting in the formation of this kind of a ene product, and one of the ethylene is lost from this beta gamma carbon is lost as a ethylene unit in this particular case. So typically an alkyne is lost during the McLafferty rearrangement. Let us take the example of this particular molecule, which is 2-pentanone. I think 2-pentanone undergoes the McLafferty rearrangement to produce acetone enol. This is a enolic structure of acetone, and the loss of ethylene unit corresponds to registering of this particular ion at 58. Between these two fragments that are produced, the charge resides with the enol, because enol will have a lower ionization potential compared to ethylene. So you remember that ions with the lowest ionization potential is what is going to be produced during the fragmentation, and this is a good example of that. In the case of butyl benzene, the carbon-carbon double bond of the aromatic ring itself acts as the hydrogen acceptor. Upon hydrogen transfer, essentially you produce the tautomer of toluene, which has the molecular peak at 92 m by z value with the loss of ethylene, which is these two carbons are lost as ethylene in this particular fragmentation pattern. Now in the case of this particular ketone, which is 1, 2, 3, 4 is butrophenone, there are two possible ways the McLafferty rearrangement can happen. Involving a carbon-oxygen bond, the McLafferty rearrangement is shown to produce an ion at 120 m by z value. Using the carbon-carbon double bond of the aromatic ring, the McLafferty rearrangement is shown to produce this particular species, which is a molecular weight of 106. Both of these are essentially even molecular weight ions. Cation radicals is what is produced. In this particular case, ethylene is lost, whereas in this particular case, the propene is lost as the fragment. The butrophenone can also undergo another type of a fragmentation, that is by alpha fragmentation, which is resulting in a stable acyl type of a cation. This is a benzoyl cation is what is produced with a mass registered at 105, and this can lose a carbon monoxide molecule to produce a phenyl cation, which is at 77. So in the mass spectrum of butrophenone, one should see 105, 106, 120 and 77 as prominent peaks. In fact, you can see this in the mass spectrum of this particular compound. Now this is the electron impact ionization mass spectrum of N-butyl benzene. Remember, we discussed N-butyl benzene and said it should register ion at 91. N-butyl benzene essentially registers ion at 91. It is fine. And this is also producing an ion at 92 because of the McLafferty rearrangement. The 91 is produced by a simple alpha fragmentation. This is a N-butyl benzene. If you cleave this fragment alpha beta bond here, it produces a benzyl cation. Benzyl cation is 91, whereas this is the tautomer of toluene, which is 92. In fact, you see 91 as well as 92. In addition to that, loss of an ethyl group, which is a 29 fragmentation, is also seen, which corresponds to the 105 as the registered ion in this particular spectrum. This is a spectrum, electron impact ionized spectrum of valeraldehyde, which is a C5 carbon aldehyde. The formyl loss, which is a 29 loss, should be seen somewhere here. 29 corresponds to the losses corresponding to the 58 peak corresponds to the loss of 29. Then the McLafferty rearrangement peak should come around 44. In fact, that is the base peak in this particular spectrum. And 57 corresponds to, this is a gamma hydrogen abstraction. One can also have alpha, beta, gamma, delta hydrogen abstraction with the loss of 28 mass units from the molecular ion peak, for example. That should result in the formation of the 58 molecular ion peak. The ion peak corresponding to 58 m by z corresponds to the delta hydrogen abstraction, where the hydrogen from this position is subtracted. The formyl loss is seen as a 29 peak, which corresponds to HCO. In fact, this alpha fragmentation results in HCO formation as the acylium cation in this particular case. So one can lose a methyl group, which is a loss of 15, which will be somewhere here. 71 corresponds to the 15 loss. One can have a loss of this butyl group here, forming the corresponding formyl cation, which is 29, for example. The butyl cation itself is registered somewhere here, probably, and the McLafferty rearrangement product is registered at 44. These are the fragmentation patterns. So what we have seen is the fragmentation pattern of some simple organic molecules. McLafferty rearrangement and alpha fragmentation, which is a simple fragmentation, is what we have seen. In the next module, we will continue with the Diels-Alder fragmentation and many other functional group fragmentations, and consider the electron impact ionization fragmentation pattern further. Thank you very much for your attention.